Hello everyone and welcome to the next Digital Days session. My name is Silas Zorn and I will moderate this webinar today. The topic of today is advancements in wireless power transfer and NFC technology. Our speaker today is Deepthi Poonacha, who is working as a design engineer at Würth Elektronik ISOs. Before we start with the webinar, short info for you. You will be mute during the webinar. This means that you cannot ask us questions via your microphone, but you have the chance to ask your questions anytime via the Q&A tool. You can find this below on the right side on the question mark button. Today's webinar will be about 30 minutes long, and after that we will answer your question in a short Q&A session. If we are unable to answer all your questions within this time, we are Deepthi will answer them via email after the session in the next days. Last information for you, you will all receive the link to the presentation and to the recording in the next days. So now I wish you an exciting webinar, an interesting webinar, and now I give it to you, Deepthi.
So thank you, Silas, for the warm introduction. So let me share my screen. Yeah, so the topic for today's webinar is advancements in wireless power transfer and NFC technology. In today's webinar, we will be talking a little bit about what is the recent advancements in wireless power transfer and how it works, and a little bit about NFC technology, and then moving on to the advantages and disadvantages of both these systems and see how we can combine them to implement it into a system implementation. This will be the highlight of today's webinar. So moving on to the agenda of today's webinar, like I already mentioned, we will talk a little bit of how exactly wireless power transfer works, a little bit about the standards defining the wireless power transfer technology. Then we get a brief overview about near-field communication technology, the principles governing NFC technology, and some standards which govern NFC technology. And finally, the highlight of the webinar is the NFC and VPT combination system implementation, where there's a short video showing how we have implemented these two technologies in one complete system. And last but not the least, there's a short product information about the portfolio of coils that we offer for NFC and VPT. So let's start the webinar today by talking about some of the examples that we see in daily life. So here are some images which you might have seen in your daily lives or use in your daily lives, like the wirelessly charging earpods, the electric toothbrush, or the charging pad where you can charge your phone, your watch, and your earpods all in one place without having the hassle of multiple cables going for every device. So all of these devices work on wireless power technology. And another common example is the wireless charging of power tools. And in this case, I can only imagine that it will be very advantageous to use a wirelessly charged tool in a construction site without having to have long cables and finding connection points. So these are some of the examples that we use every day where wireless charging is implemented. And of course, there are many other examples that use wireless power transfer. And this is only to show the big advantage of using wireless power transfer instead of the long hassle cables. So how does exactly wireless power transfer work? So as you can see in the image, there is a base station, which is the transmitter, and then a mobile device or the receiver. So the transmitter is always your charging pad, which you connect to the power source, and your receiver is always the application or the end user application, like the mobile devices in this case, which you place on top of the charging pad and enable the wireless power transfer. So how does it actually work? So from the power source, there is an alternating current which flows into the coil. And this alternating current induces a magnetic field, as you can see, the gray magnetic field lines in the image. And this magnetic field then induces a current in the receiver device when it is brought closer to the transmitter side and generates a current here in the receiver, which then powers up the battery or the electronics at the end user application. So this is a principle of electromagnetic induction, and the wireless power transfer works on this principle. And as you can see here, the magnetic field lines are limited to this closed space, and that is why you cannot charge the mobile device at a very long distance. If you move your phone farther away from the transmitter coil, then the magnetic field strength will also reduce and the coil will not charge. The typical frequency range of wireless power transfer is why defined between 100 kilohertz and 200 kilohertz. And it's a short range of transfer of power. And the powers capable of transferring using wireless power transfer is up to a few kilowatts range, depending on the application. The type of communication that is possible in the wireless power transfer is low in-band communication with a low data rate of only up to a few kilobits per second. And like I already mentioned, the power transfer via inductive coupling can happen at short distances only, so the range is limited to a few millimeters. So now having learned about the principle of wireless power, let us go on to see what are the advantages and disadvantages of wireless power. Like I already mentioned in the previous slide, we can already sum up some of the advantages and disadvantages. So the first, we start with the advantages, where we see that, of course, high power levels up to kilowatts are possible, which are dependent on the application. And there's no wear and tear of any charging cords due to mechanical stress of daily plugging it and unplugging it. And we can make easy designs with hermetically sealed devices, protecting it from moisture in the environment, which may result in corrosion later, and also to eliminate connectors or power ports. And like every technology, there are some disadvantages here as well. And the disadvantages is that it has low data rates of only up to few kilobits per second. That means very less data can be transmitted using wireless power transfer. And it is inefficient to transfer power over long distances. So you cannot transfer power over 1 kilometer or something like this when using wireless power transfer. Next, we talk a little bit about the Wireless Power Consortium. So like every new technology that is developed, there has to be a body governing this new technology where they define certain rules and standards so that we can design this new technology using these standards, thereby making it safe for everybody all over the world to use it. So similarly here, for the wireless power devices also, there is a body which is called as a Wireless Power Consortium, which has developed some standards for the mobile phones and handheld devices up to a power level of 15 watts. This standard is called as the Qi standard, and it is the symbol, as you can see in the figure 7, looks like this. And if you find any devices with this type of a symbol, then you know that that device is Qi certified, and it is safe to use along with your smartphone or your handheld device for charging. Another standard is also defined by the WPC, and that is called as the Key standard, which is defined for transmitters which can transmit high power levels up to 2.2 kilowatts for smart cordless kitchen appliances. So this has been defined and it is still in development, and the symbol looks like the figure 8. So in the future, when you see this figure on your smart kitchen appliances, then you know that they are key compliant. So what are the standard specifications defined under the Qi standard? So they are as follows. As you can see, the operating frequency is defined at only 87 to 205 kilohertz. And there are 3 power profiles which are defined by the WPC. the basic power profile for devices operating up to 5 watts, the extended power profile for devices operating up to 15 watts, and the magnetic power profile for devices operating also up to 15 watts. And as you can see, the magnetic power profile is fairly new. So let's talk a little bit about the advancements in this wireless charging standard and technology. So this year, the Wireless Power Consortium has released the Qi2 wireless charging standard, and this is mainly based off on the Apple's MagSafe power profile. And the symbols are as shown in figure 9 and in figure 10. So in the future, all the new devices or mobile phones will have this symbol to show that they are Qi compliant, or the transmitter, the chargers will have this symbol to show that they are Qi2 compliant. So what exactly is new in Qi2 is that the Qi2 is the magnetic power profile, where they are using magnets to align the transmitter and the receiver on top of each other and reduce misalignment between the transmitter and the receiver. We will see a little more about this in the next slides. The Qi2 standard can also include products that don't have magnets, and they are then defined by the figure 10. The symbol shown in the figure 10 is to show the devices which are Qi2 certified but do not have magnets. The operating frequency for this Qi standard is defined at 360 kilohertz. And here, if you notice the difference from the Qi and the Qi2, the Qi was defined only up to 205 kilohertz, and here the operating frequency is defined at 360 kilohertz. And the magnetic power profile, the transmitter of the magnetic power profile offers a guaranteed 15 watts power delivery system. So now, having had a glimpse of what exactly Qi2 is and how it looks like, let's go a little bit deeper to see the advantages of Qi2. So what's so big about this Qi2 power profile? So from the images, you can already see the difference between the Qi2 power profile and the legacy power profile. So the Qi power profile is called the legacy power profiles. And you might all be familiar with these type of chargers at your home for your phones, where you have to place them on the table or on a flat surface connected to the power supply and place your mobile phones on top exactly for it to charge. And if you move it slightly away from the charger, then there might be very slow charging that takes place, or it might not charge at all. But in the new Qi2 power profile is then this magnet which is present in the transmitter, and also a magnet present on the receiver side on the phone. And you can pick up your phone while it's charging and work on it. It doesn't, because it is already attracted to the magnet on the receiver, and it holds, and the phone is aligned, and it is charging perfectly. And it is faster. So it has 4 times faster authentication compared to the Qi standard. And it reduces misalignment between the transmitter and the receiver, as you can see in this image here. So when the coils are perfectly aligned, then it should be the blue arrow, but because that means they are both centered, and the red arrow is less efficient. And here, when they are together, when they are aligned perfectly on top of each other, then they are more efficient. And the frequency, the reason for having the Qi2 at 360 kilohertz frequency, make it more easier to use key fobs in the vicinity of the Qi2 devices. In the past, it was observed that wherever the Qi devices were used, key fobs or any other wireless appliances would have certain interference because of the frequency range and would not operate properly. And in this case, that's the reason they have increased the frequency to 360 kilohertz, so that the key fobs which operate at a much lower frequency, which was falling in this range of the Qi standard frequency, was having a lot of interference. And in this case, this is also avoided. So as you can see, the Qi2 profile has a lot of advantages compared to the legacy power profile. So how does a coil defined or designed with the Qi2 specification look like? So the specification has not yet been publicly released by the WPC, but we at Würth, since we are a member of the WPC, we have a preliminary spec that we have received, and we have designed our own transmitter coil that is following the Qi2 specifications. And it looks like this is the small breakup of the transmitter coil. The part number will be released on our website as soon as the WPC makes the release publicly. So the coil consists of the top enclosure and the bottom enclosure. This is an extra additional component in the coil itself. And like I mentioned before, the coil has a magnet array and a permeable shunt magnet to hold the magnetic array pieces together. And then we have the coil itself and also then the ferrite piece as well. So all these parts together make up the transmitter coil of the MPP design defined by the Qi standard. So now, having had a glimpse of how wireless power transfer actually works and what are the standards governing wireless power technology, and also looking at the advantages and disadvantages, let us move on to the next technology, that is the near field communication technology. So I'm very sure that all of you have observed near field technology or have used near field communication technology in your daily lives, but maybe you are simply not aware of it, that it is falling under this category of technology. So to have a look at it, some examples, as you can see in figure 13, you use your phone to make a payment or to download your boarding pass and take it with you and use it in the counter to check in, use your tickets on your phone to enter into the train stations and make payment via phone. And all of these applications are working on NFC or near field technology. So what is near field technology and how it actually works? So like the name itself says, it is a short range standardized high frequency technology, and it has a very short range of only up to a few centimeters, which is still bigger than the wireless power transfer distance of transmission. And here the NFC is based on the RFID type of technology. The frequency band, as you can see, is much higher than the wireless power transfer, and it can charge up to only 1 watt. And the data rates under near field communication is between 106 kilobits per second to 424 kilobits per second, which is already a lot more than the wireless power data rates. So some properties of the NFC include remarkably fast startup. You must have already observed this when you're making payments with your phone. It's very fast. There's a very short connection time and power sensing and a small data payload. And this remarkably fast startup also makes it more secure to do these payments using NFC technology. So going a little bit deeper into how NFC technology actually works. So here, as you can see, there is the host PC, which is connected to the contactless reader or the polar or the initiator, that is basically the transmitter. The coil of the transmitter and the coil in the receiver is called as the antenna in the NFC technology. And the NFC tag, listener, or target is the receiver part of the NFC system. And the transfer of power and data happens via electromagnetic field, as you can see the red waves here. So the transmitter sends power and data to the NFC tag or the listener. The information is received on the card side, and then it sends back the data via the electromagnetic field to the contactless reader, which is then transmitted to the host PC. So this is the operation of NFC, and this is typically used for reading contactless tags or smart cards. Now, having had an introduction of NFC, let's go a little bit deeper and see what are the different types of modes that are used in NFC. So we have the 3 main operating modes in NFC. That is the reader or writer mode, the card emulation mode, the peer-to-peer mode. So in the reader or writer mode, the communication is enabled by the NFC initiator, like a mobile phone, like we just now saw with the NFC tag, for either reading or sending data from those tags. The card emulation mode is where the NFC device emulates the behavior of a contactless card and following one of the standards of NFC. And in the peer-to-peer mode, it is used to establish a two-way communication between a pair of NFC-enabled devices. And this we can see a little more clearer in this pictorial representation. So this is our transmitter for now, and here are the three different type of modes and some examples to show how peer-to-peer card emulation and the read and write mode actually works. So in the peer-to-peer is when you're sending data from one NFC device to another NFC-enabled device, and it is in the active mode. So you're sending data from your laptop to your phone, or you're controlling your washing machine via your phone or your camera via your phone, and this is the peer-to-peer mode. There's exchange of data between the two devices. The card emulation mode is very common. You might have all observed in your daily lives. You're using your phone to go through the check-in in the railway station or for your boarding passes, or you're using the phone itself to act as a card, which emulates the behavior of a card when you're paying at a supermarket or a different shopping store. The read or write mode is where you can scan the code or a contactless card and then get the data or read a data or write data, and this is then defined as the read or write mode of the NFC technology. So like every other new technology, there are standards for the near field communication technology as well. And this is defined by the NFC forum. And here we have the different type of standards. And we are following the type 1, the ISO IEC 14443A. And we are using this standard, which is very commonly used for most of the devices as well. Even in our system implementation, we are using the same type of standard. So this has a standard frequency of 13.56 megahertz, a data rate of 106 kilobits per second, an amplitude modulation, amplitude shift keying modulation from the reader to the tag, and the load modulation from the tag to the reader. So now we have had an overview of both these technologies, and we can sum up what are the advantages and disadvantages of both these systems. So the disadvantage in the VPT was that it had very low in-band data rates of only up to 1 kilobits per second. And in the NFC, it was that it can transfer very low powers of only up to a few watts. And in the VPT, the advantage was that it can transfer high power. And in the NFC, the advantage was it can transfer high data rates. So here in our system implementation, we have combined the two advantages of high data rates and high transfer powers and put it together to build up a simultaneous VPT NFC combination system. So normally the case is NFC is used in the slotted form where there is only NFC turned on and VPT is turned off. And in Würth Elektronik, we have developed a simultaneous VPT NFC system where both these technologies operate at the same time without any interruption. In the figure 16, you can see an example of our combination coil where the ferrite is the carrier, the VPT coil is the Litz wire that you can see very commonly in all of our coils, and the copper wire are surrounding this Litz wire is the NFC antenna, which is used for NFC communication. In figure 17, we have a block diagram showing our system implementation. So the green arrow represents the NFC system buildup, and the red arrow represents the wireless power transfer system buildup. So for the wireless power transfer system, we have just used our 200-watt development kit, which you can also check on our website. It has reached end of life, but there are a lot of materials still available to build up your own development kit. And in our NFC block, we have the microcontrollers and NFC interfaces, where we will be going in the further slides deeper into each block and looking at what is happening. So this is the initiator block. So in the initiator block, we have a power source for the microcontroller. That's the 5 volts. And as a load, we have connected also a sensor to the microcontroller. We have simply used the Arduino Mega microcontroller and the NFC interface. We have used the Adafruit PN532 NFC RFID shield. And for the sensor, also we have used a time of flight sensor from the Adafruit. So we have used all the easily available device components from Arduino and Adafruit, so anyone can build it up themselves. The target block is the exact same replica of the initiator block, except that the microcontroller is the Arduino Uno revision 3, and we have a display board, which you can also pick up from Adafruit, and uses I2C type of communication. So the 200 watt kit transmitter is used as the wireless power transmitter, and the receiver of the 200 watt development kit is also used for the receiver side here. Then we have a very special filter matching network. This is also designed and developed by Würth Elektronik. As you can see in the block diagram, there is a filter matching network in the NFC initiator side and the NFC target side. And the reason is that the impedance of the NFC interface chip is at 50 ohms. The output impedance is at 50 ohms. And we have to match this output impedance with the impedance of the antenna at the NFC side of the coil. So in order to match these two impedances, we have developed our own differential filter matching network. It is a differential filter matching network because the output of the NFC interface chip is also differential, and this is very commonly used in order to reduce the noise in circuits. So we have developed a filter matching network for differential circuits, and this can be read more on our app note on the website. In the filter matching network, we have a second order low pass filter at the beginning, followed by a capacitive impedance matching network and some damping resistors. And this is then the next part is the equivalent antenna circuit. So impedance matching is very important in this system, because if impedance of the NFC chip and the NFC antenna are not on the same value, then the power transfer will not happen and the whole system will not work simultaneously. And the filter is also important to remove unwanted harmonics and also to improve the radiated field between the two coils of the transmitter and the receiver. Then after the hardware is defined, we need software to make the whole system work. And here is a short workflow overview of how the software is working. So an initiator writes a request to the target. The target then accepts this request, and the time of flight sensor on the initiator side then sends this data to the NFC interface on the initiator, and the sensor gets the data written on the target. Then the target NFC sends the written data back to the display, and you can finally see the data on the display. And there is the target pings the initiator every few seconds to see if there is a new request coming in. So this is a very simple software workflow, which you can also find on Adafruit to help out if you're starting on your own a project to develop a VPT and NFC system simultaneously, and you can get it working. So here is a short implementation video of the system, and before I start it, I would just like to explain what you see on the screen here. So if you remember the block diagram that I just now shared, the 200 watt kit transmitter is on this side and the 200 watt kit receiver is here. You can also read it on the notes, labels written below each component. And the NFC matching circuit is separately built, as you can see, which consists of the filter matching network, the differential filter matching network that I just now showed. the NFC and VPT combination coil is placed in this structure in the middle. There is a distance of 6 millimeter separation between the two coils of receiver and transmitter. The microcontroller on the transmitter side is connected here, and it is powered up externally through a 5-volt cable, and the 200-watt kit is also powered up externally. But as you observe here, the MCU on the receiver side and the display and the NFC board is all powered up by wireless power charging. So the wireless power kit is powering up all these devices on the right side, on the receiver side, and only the transmitter side is powered up externally. So let me play the video, and you can see the value on the sensors here. So when this is the time of flight sensor is placed on the transmitter side, as I explained in the block diagram. So when there is an object placed close to the sensor and moved away, the value is recorded and displayed on the display here. So to play the video now, as you can see, the hand is being placed close to the sensor, and you can see the distance of the object from the sensor. Let me play it one more time. Yeah. So this was the system implementation of wireless power transfer and NFC together, that we have done it simultaneously, and we can use this in many applications. So a tabulation of the results of the system implementation. So the type of wireless power kit that we have used is our 200-watt development kit. The combination coil that we have used here is also available on our product portfolio online. The distance of separation between the transmitter and the receiver is 6 millimeters, and the NFC data rate which we have used here is 106 kilobits per second for the sensor. The reflection coefficient that we measured after building up our filter network was minus 35 dB, and with an error rate of less than 5%. So some of the future work for us based on this system implementation is to try and achieve a higher data rate using NFC of around 424 kilobits per second, and to build up the filter network and the VPT transmitter board together as one VPT system. So this is a short glimpse of our portfolio. Here are our combination products, which uses VPT and the NFC coils together. You can find this on our website. These are some useful links to the app notes, which discusses about the impedance matching for NFC applications, some high proprietary wireless power transfer solutions, high power wireless transfer for industrial environments, wireless power charging coil changing considerations, which is important when you're designing your own coil, and some wireless energy transmission, where it is a short discussion about coils as key components and how they are useful for us. So hope you enjoyed the webinar and learned something new, and thank you.
So now I think we can start. Deepthi,
Yeah.
Are you ready for the questions?
Yes.
Cool. First question, is it permissible to use the VPT files for data communication, or does not change the regularity regime for it?
We can use the VPT to transfer data, but as you already saw from the presentation, the data rate in VPT is very low. So you can transfer very low data of only up to 1 kilobits per second. And the regulatory regime for VPT products is always the red regulation that is there, the red certification regulation that is there for all radio devices.
Okay, thank you for the answer. So we continue to the next question. Will the NFC coil be affected by VPT when high power is transmitted?
So in our system implementation, we have used the NFC only for the data transfer, and wireless power is used only for the power transfer. So the NFC will not be affected by high powers. For example, we have also designed a kitchen coil which can transfer up to 2.2 kilowatts. And here NFC is also inside, as in it's a combination coil, so it is not affected by high power transfer.
Okay, thank you for the answer.
Mm-hmm.
Next question. What is the typical efficiency of the maximum power transfer?
Can you please repeat it, Silas? I couldn't hear you.
Sorry. What is the typical efficiency for the maximum power transfer? Sorry.
Yeah, so the maximum efficiency would be around 80%. That is what we have measured on our 200-watt development kit. But it is completely dependent on the other application that you are integrating the wireless power coil inside. So from our observations and measurements of our 200-watt development kit, we were able to reach around 85% efficiency.
Thanks for the answer. So we continue directly to the next question. What about the EMI/EMC compliance?
So like I already mentioned, it falls under the RED directive, and you cannot determine the EMI compliance for a single coil. It has to always be measured as a whole system. So if you're integrating your wireless power coil in a system, then the EMI measurement for the whole system is taken into consideration. And our coil, that we have also done some measurements for the EMI for the conducted and the radiated emission from our coils, and they are within the RED directive standards.
Thank you for the answer. Now we can to the next question. Is there also a plan to combine NFC and VPC to charge small devices via a smartphone while communicate with them?
Yeah, definitely. We have also many customers who are interested in this kind of design because it's very advantageous to use VPT and NFC together, where you can use the advantage of one technology and use the advantage of another technology together. So you can use wireless power to charge your phone and use NFC for data communication. It is possible.
Okay. Cool. Next questions, I would say the last one. What about the efficiency of 2.2 kilowatt and how do you manage the thermals?
For this 2.2 kilowatt, it is a key design from the VPC standard. So the efficiency for this is around, we haven't actually measured it completely because it is still under development, since the spec also has not yet been released by the WPC. And the thermals, we have a special design where there is a big chunk of ferrite pieces added to the coil, and this helps a lot in thermal dissipation. And when it is also added into the system for the kitchen appliances, they have additional materials around which will help in dissipating the heat easily.
Cool. Thank you. Thank you for the answers for all the questions. Thank you for your questions. Yeah, so now we are finished with that session of the Digital Redays. So thank you for your attention. I hope you enjoyed it, and hopefully we see you on the next session of the Digital Redays.
Yeah. Thank you.
Goodbye.